In the previous videos, we covered the photovoltaic side of this model in detail. The PV generator, the perturb and observe algorithm, the boost converter, and the voltage-oriented control that manages the grid-connected inverter. In this video, we're going to focus on the second energy source in this hybrid system, the wind turbine generator, labeled WTG1. Just like the photovoltaic string, the wind turbine generator produces DC power and feeds it into the same shared DC link right alongside the output of the PV boost converter. A second, identical wind generator unit, labeled WTG, contributes to this same DC bus as well. This means the photovoltaic array and the wind turbines are both charging the same DC link, which is then converted to three-phase AC and exported to the grid through the inverter we already explained. Let's open up the WTG1 subsystem and go through it step by step. The first block represents the wind turbine itself, modeled here as a Savonius type turbine. It has two inputs, the wind speed in meters per second and the generator speed, also called omega, measured in radians per second. Its two outputs are the mechanical torque, labeled Tm, and the mechanical power, labeled Pm. These two outputs describe how much mechanical energy the wind is delivering to the generator shaft at any given moment. Inside this turbine block, the model follows the standard aerodynamic power equation used for wind turbines. The available power in the wind is proportional to the air density, the swept area of the rotor, and the cube of the wind speed. This cubic relationship is very important. It means that even small changes in wind speed cause large changes in the available power, which is why wind energy systems require fast and responsive control. However, not all of this wind power can be captured. The fraction that the turbine actually converts into mechanical power is described by the power coefficient called Cp. This coefficient depends on the tip speed ratio, labeled lambda, which is the ratio between the rotor's tip speed and the wind speed. In this model, the tip speed ratio is calculated by multiplying the generator speed by the rotor radius, and then dividing by the wind speed. The relationship between Cp and lambda for this Savonius turbine is implemented using a cubic polynomial, shown in the block labeled Savonius. This polynomial was fitted from the turbine's characteristic power curve, and it allows the model to estimate how efficiently the turbine captures wind energy at any operating point, without needing a complex aerodynamic simulation. You will also notice several blocks labeled avoid division by 0, placed at different points in this subsystem. These are safety saturation blocks. Since the tip speed ratio calculation involves dividing by wind speed and the torque calculation involves dividing by generator speed, both of these values could become 0, especially during startup. Dividing by 0 would cause the simulation to fail. These protective blocks simply clamp the denominator to a very small non-zero value, keeping the simulation numerically stable. Once the mechanical power is calculated, the mechanical torque is obtained by dividing the mechanical power by the generator speed. This torque, Tm, is then sent out of the wind turbine block and used to mechanically drive the generator. That generator is a permanent magnet synchronous machine, referred to as a PMSM. The mechanical torque from the turbine drives this machine, and in return, the PMSM reports its rotor speed back to the turbine block. This creates a closed mechanical loop. The turbine produces torque based on the current generator speed, and the generator's actual speed depends on how much torque it receives. This is exactly how a real wind turbine and generator interact. On the electrical side, the PMSM produces a three-phase alternating current output on terminals A, B, and C. Because the wind speed and generator speed constantly change, the frequency and amplitude of this AC output also vary, unlike the fixed 50 Hz grid frequency. To make this variable AC power usable, it first passes through a three-phase diode rectifier, which converts it into DC. A smoothing capacitor, labeled C2, is placed right after the rectifier to reduce ripple in this rectified DC voltage. This rectified DC voltage then feeds into another boost converter stage, built from an inductor labeled L, a diode, an IGBT switch, and an output capacitor, labeled C1. This is the exact same boost converter topology we explained in detail for the photovoltaic system, Energy is stored in the inductor while the IGBT is on, and released to the output through the diode while the IGBT is off, producing a higher DC voltage at the output than at the input. But here is an important difference. In the photovoltaic system, the boost converter's duty cycle was controlled using a PI controller and a perturb and observe algorithm. In this wind turbine system, the control strategy is different. Let's look at the control subsystem to see how. The control subsystem implements what is known as a power signal feedback method for maximum power point tracking. Instead of perturbing the voltage step by step, this method directly calculates the optimal power the turbine should be producing, based on its current generator speed. This optimal power reference is computed using a cubic function of the generator speed. The constants in this formula are derived from the turbine's known optimal power coefficient, its optimal tip speed ratio, the air density, and the rotor geometry. In simple terms, this equation predicts, for any given generator speed, exactly how much power the turbine should ideally be producing if it were operating at its maximum efficiency point. At the same time, the controller takes the actual measured electrical current which delivered by the generator, again using division protected by an avoid division by zero block for safety. The optimal reference power divided by the measured current to calculate the reference voltage. These two values, the optimal reference voltage and the actual measured voltage, are then compared. The difference between them represents the voltage error. Instead of feeding this error into a PI controller, this model feeds it directly into a relay block, which acts as a hysteresis comparator. The relay switches on when the voltage error rises above 0.01 and switches off when the voltage error falls below -0.01. This produces a fast, bang-bang style switching signal that directly drives the IGBT. In other words, whenever the turbine is producing less voltage than its optimal reference, the relay turns the switch on, increasing the electrical loading on the generator and pushing its operating point back toward the optimum. Whenever the turbine is producing more than necessary, the relay turns the switch off. This constant switching keeps the wind turbine oscillating tightly around its maximum power point, similar in spirit to the perturb and observe method used for the photovoltaic array, but implemented here through direct voltage comparison and hysteresis switching, rather than incremental voltage steps. Once boosted, the output of this converter, through connection 1 and connection 2, joins the same DC link as the photovoltaic boost converter. From that point onward, the combined DC power from both the sun and the wind is processed exactly as we described in earlier videos, regulated by the voltage-oriented control loop, and converted into clean three-phase current that is injected into the grid. In summary, this wind turbine subsystem models the complete energy conversion chain from wind to grid. The Savonius aerodynamic model converts wind speed into mechanical torque and power. The Permanent Magnet Synchronous Machine converts that mechanical energy into variable AC electrical power. A rectifier and boost converter convert that variable AC into stable, boosted DC. And a power signal feedback controller with hysteresis switching continuously drives the system toward its maximum power point, regardless of how the wind speed changes. Together with the photovoltaic string we explored earlier, this creates a true hybrid renewable energy system, combining solar and wind generation on a single, shared DC bus, feeding a common grid-connected inverter. Let's now look at the scope results for this simulation. The top trace shows the DC link voltage, labeled V. At the very start of the simulation, you can see a sharp inrush spike, where the voltage rises quickly and briefly overshoots to about 485 volts, occurring at around 48 milliseconds into the simulation. This kind of overshoot is completely normal during startup. It happens because the DC link capacitor is charging up for the first time, and the control loop has not yet stabilized. After this initial spike, the voltage settles down and regulates around its steady-state target. Looking at the signal statistics, the mean value of the DC link voltage across the whole simulation is about 394 volts, while the median is about 402 volts, and the root mean square value is about 397 volts. The fact that the median and our M-South values are close to each other, and both sit near 400 volts, confirms that after the initial transient, The voltage spends most of its time regulated tightly around its 400-volt reference. The bilevel measurements panel gives us more detail about this startup transition. The voltage rises from a low level of about 2.4 volts up to a high level of about 400 volts. This rising edge takes about 34 milliseconds to complete, which corresponds to a slew rate of about 9.3 volts per millisecond. Only one rising edge is detected, and no falling edge, which confirms that the voltage rises once during startup and then remains stably at its regulated level for the rest of the simulation. The cursor measurements at the bottom of the statistics panel confirm just how stable the voltage becomes later in the simulation. At 246 milliseconds, the voltage measures about 402.9 volts. Later, at 680 milliseconds, it measures about 402.4 volts. Between these 2 points, spaced about 433 milliseconds apart, the voltage changes by less than half a volt. This extremely small variation shows that the voltage-oriented control loop is successfully holding the DC link voltage steady, well after the initial startup transient has settled. Now let's look at the middle and bottom traces, which show the three-phase current and voltage waveforms. In the middle trace, we can see a similar pattern to the top trace. At the beginning of the simulation, there is a large transient, with the three-phase waveforms oscillating with much higher amplitude, reaching up to about 150 units in both the positive and negative direction. This reflects the same startup inrush behavior seen in the DC link voltage. Very quickly, however, these oscillations collapse down into a small, tight, continuous ripple band centered around zero, indicating that the three-phase quantity reaches a stable, balanced, steady state shortly after startup. The bottom trace shows a three-phase waveform as well, but here the switching ripple remains visible throughout the entire simulation, oscillating steadily between about plus and minus 200 units. This continuous high-frequency ripple is expected, since it reflects the fast switching action of the inverter's IGBT devices, which operate continuously throughout the simulation to synthesize the desired output waveform. Overall, these three scope traces tell a consistent story. The system experiences a short but expected startup transient, during which the DC link voltage briefly overshoots and the three-phase quantities show large initial oscillations. Within a fraction of a second, the control system brings everything under control. The DC link voltage settles tightly around its 400-volt reference, and the three-phase waveforms reach a clean, stable, periodic steady state, with only the expected high-frequency switching ripple remaining visible for the rest of the simulation. That wraps up the simulation walkthrough. If you found this video helpful, please consider subscribing to the channel and hit the like button. It really helps the channel grow and makes this kind of detailed, in-depth content possible. If you know someone who is studying power electronics, renewable energy systems, or Simulink modeling, feel free to share this video with them. It might save them a lot of time. If you have any questions about this model, or if there is a specific block or control strategy you would like me to explain in more detail, leave a comment down below. I read every comment, and many of the upcoming videos in this series come directly from viewer questions and suggestions. Also, make sure to check the description box for links to related videos in this series, as well as any downloadable resources for this model. Thank you so much for watching, and I will see you in the next video.